Remember how the first thing that was important to figure out after we defined a derivative on a lattice was lattice Laplacian, basically the square of the derivative. That operation is very important because in physics we have it all the time. It has to do with harmonic oscillators, which have second derivative in acceleration, time acceleration, second derivative in the spring constant. So it's a very basic thing in much of physics. Also in engineering, when you're computing cost functions, typically they are quadratic cost functions, the simplest one. And they will have lattice Laplacian stuck into them. And you know, lattice Laplacian was very obvious. This was a first order derivative. And if I took a field and multiplied it by its transpose, this is just a vector, and I used integration by parts or transposition to move this in, I got the definition of what's Laplacian in continuum, second order derivative, which is product of these two terms, which is easily evaluated. And it turns out to be a very nice and very intuitive object. It just looks at me and looks at my two neighbors, and then compares the sum of the two neighbors to me. You know, are they more powerful, less powerful on average? And that measures some or other penalty I'll have to pay for being too high, too low, you know, away from the average. So Laplacians punish anybody who is not average. They tend to damp it out. So the diffusion equation will have Laplacians, which will remove all the kinky stuff and make it all very smooth. They're every place. So it's a nice, obvious thing. You know, I'm here, I compare myself to neighbors. But then if you look at any natural function of Laplacian, so here is a function that appears all the time. It's called Propagator. Or it's called, you know, energy of harmonic oscillator. You compare the inertia to the acceleration, second order term in it. And when you write it as matrices, you can write it as a power series. And you find out that this is a very horrible and complicated matrix to evaluate because it fills out all the entries in a matrix. It's very non-local. So that's a big problem about derivatives when you think of them seriously. It's not obvious when you do this in continuum limit, but discrete decision make it very clear that inverse of the derivative is, you know, let's say integral, and that integrates over everything. So, you know, how do we compute this stuff? Well, it turns out if you have translation invariance, things are incredibly simple. So now let's go back to our technology of discrete Fourier transforms and look how we can use this method of projecting things onto Fourier components. And that's called lattice. And that's called lattice Laplacian diagonalization. And you use it all the time when you're learning engineering and physics, electrical engineering, data science, rocket science, whatever. And you have to understand that it only works when you have translational invariance. When you don't have it, when you have a solution, let's say that's turbulent, the Fourier transform might not be much more insightful than the original problem. You have to think where it's useful for you, but here is what we can do with Laplacian. So Laplacian, as I showed you here, is a sum of translate right, translate left, that's inverse, compare with me at identity and sum up over all directions. That's what Laplacian. So let's just do it in one dimension because it turns out summing up is very easy. So it's a matrix. It has two indices. It has this average of my neighbors, left and right neighbor. Remember, these are matrices that tell me what the neighboring state, entire lattice state is. The n by n matrices, they can be big. Minus me, minus identity. I measure the curvature. Are they above me, below me, or are we all equal and flat? Then, there is 2 over lattice spacing here. And now, if I apply my eigenvector on the right-hand side, then I know that this will be replaced by eigenvalues of that eigenvector. And to get this component of lattice Laplacian, I put Hermitian conjugate of k eigenvalue on the left-hand side. So here I have a matrix, and I sandwich it, project it onto these two things. Now, I know that these are eigenvectors or translation operators. So I'll get a number times translation operator. And multiplying by this, I find out that Laplacian in Fourier space has components only on diagonal where k equals k prime. That's the whole point. That's why we learn Laplacian transforms. So, we get here F Hermitian conjugate k. So the two eigenvectors, and they just give us Kronecker delta, they're normalized correctly. Then there is 2 over a square and this returns the eigenvalue, but those are roots of unity, right? So they're e to the I 2 pi over n to kth power, primitive root. And, and this one is a complex conjugate of that one. It's inverse, so it has a minus up here. 2 pi over n times k divided by 2 minus unity on one-dimensional space is just a number 1. So this is called cosine. So I get 2a square cosine 2 pi k over n minus 1 times Kronecker delta. In other words, what used to be a horrible calculation in configuration space, because matrices that constructed this particular typical calculation matrix function filled out the entire space. When I go to the Fourier space, I just get n numbers on a diagonal. Laplace operator has only entries on the diagonal, and they're real numbers. And they're real numbers because Laplace was constructing by taking a derivative times transpose. So under transposition, that's the same object. It's invariant on transposition, which means in terms of matrices that what's on diagonal has to be real. What's off diagonal has to be complex conjugate of each other, but we are only on diagonal. And that's why you use Fourier transform all the time in all kinds of calculations.